This is just continuing the log rule. Sometimes your log rule problems are a little bit disguised. In this case, that's definitely true. So if the numerator is of a degree that is greater than or equal to the degree of the denominator, you can use long division or synthetic division to rewrite the integral and potentially then use the log rule. So an example of that is going to be this polynomial right here. Notice that if I took the derivative of the denominator right now, I just have 2x, which is clearly not that. I don't have just one term in the denominator, so I can't split this up. So something else has to occur here. So what I'm going to do is try doing long division or synthetic division. And in this case, because of the fact that I'm not exactly sure what to do with that denominator with a coefficient, or not a coefficient, but a degree of 2 instead of a degree of 1, I'm going to use long division here. So x squared plus 1 divided into x squared plus x plus 1. Remember, when you're doing long division or synthetic division, if that's what you choose to do, you have to include all the missing terms with a 0 coefficient. So if we didn't have that x term right there, we'd have to put a 0x in to account for it. All right, so now I'm just going to do the long division. What times x squared gives me x squared? The answer, of course, is 1, so I write that there. And then I distribute. 1 times x squared is x squared. 1 times 1 is 1. I draw my line, and I subtract. The way that I subtract is I change all the signs, and I add. So we're left with an x right here. That's my remainder, and the way that you learned how to write the remainder was to write the sign of this guy, which in this case is plus, the remainder divided by what you were dividing by in the first place. We did this process when we were looking at slant asymptotes. Hopefully you kind of remember that. Okay, so now what I've done is I've carried out this division right here, which means I can rewrite this integral as the integral of 1 plus x divided by x squared plus 1 dx. So the nice thing now is I can split this into two separate integrals. Integral of 1 dx plus the integral of x over x squared plus 1 dx. Well, the integral here I can do easily. I just get x plus, and if you notice the way this is written now, it's almost the derivative in the numerator, okay, of the denominator. In order to fix that, I need to put a 2 there, because the derivative of the denominator is 2x, and now I have the derivative of the denominator sitting in the numerator, which means I just need the 1/2 out front to keep this thing in balance. And so now, using the log rule, I have the 1/2 times the natural log of the absolute value of x squared plus 1 plus c. Now, do I need the absolute value? In this case, no, I don't. Because no matter what I use for x, even if it's negative, I'm going to square it and it'll become positive, and then I'm adding 1 to a positive number. I'm always going to be positive. So you're going to see, if this was in the back of the book or on a test or something, you won't see the absolute value there. You'll see parentheses, which, even though it's still putting some sort of grouping symbol on there, is simplified compared to the absolute value. So that's your answer. So we can also use the change of variables that we learned previously in chapter 4 to take care of an integral like this. So what we're going to want to do is pick a u. In this case, what should we pick probably for u? Yeah, the inside function, x plus 1. So let u equal x plus 1. When I'm integrating, I don't write u prime. I write du. I use the differential form. du equals dx. All right, so now this turns into u. This turns into du. I got that x hanging out there, so got to solve this equation for x. I get u minus 1. All right, so let's rewrite this now and see where we're at. Du. Now what?
I got it. Okay, so we're going to throw that 2 in and then split it up.
Throw the 2 in and split it up.
Yeah.
Okay. So you mean distribute the 2 in.
Yeah.
All right. So I'll have the integral of 2u minus 2 divided by u squared du. I threw the 2 in. Okay, now I'm going to split it up because I only have one term in the denominator, and that's usually a good route to go. So now I have the integral of 2u over u squared yeah, it did get squoze in pretty good. And now what? Now we can separate this into 2 different integrals. Reduce. Well, let's not do too much at once. Integral of we can get rid of the 2. Fancy it out. How about factor it out? Sure, this is a constant. We did throw it in for no reason. We could have left it, actually we could have taken it out completely right here. But that's okay, we didn't know that. So I can factor this 2 out here. Integral of 1 over u du. I'm splitting this integral up as well. Minus 2 integral 1 over u squared du. We can go?
The 2 integral 1.
This first guy.
Yeah, that one.
Yeah.
Turns into 2 natural log of u.
Why? Yeah. This is the log rule right here. The derivative of the denominator is sitting in the numerator. The derivative of u du is 1. So there it is. U prime over u already. Okay, so what do we get? But u is? Good. This is u to the negative 2 here. Yes. 2 times, you integrate that. There's no need for natural log here. This is an exponent that we can add 1 to and not wind up with division by 0. So we add 1 to that and we get u to the negative 1 divided by the new exponent, negative 1. Plus c. Okay, so we already know that one. 2 natural log absolute value x plus 1. Simplifying this, I have a negative 2 divided by a negative 1, which is a positive 2. A u to the negative 1 means u in the denominator, but u is x plus 1. Plus c. We don't? We can? You might see this with the 2 factored out here. 2 times the natural log absolute value x plus 1 plus 1 over x plus 1 plus c. But yeah, I think that's probably good enough right there. All right, integral of 1 over x natural log x in the denominator. Try it. With a problem like this, and you were trying to use a u substitution, you got to pick a good u. There's the trivial one where we let u equal x. That doesn't do me any good. All I did was trade one variable for the other and I didn't change anything. So that one's not going to work. I get du equals dx, big deal. I still have a situation that I don't know what to do with here. All right, so maybe then you were like, well, if I go with u equals the entire denominator, then I wind up with 1 over u, which I do know how to integrate. So let's let u equal x natural log x. But now to find du, what do I have to do? The product rule. So that would be f prime is 1 natural log x plus this guy times the derivative of the natural log of x, which is 1 over x. So that's all dx. So now I have du equals natural log x plus 1 dx. And I still have this natural log thing. So even if I solve this for dx, I'd have an x sitting here still. But the natural log of x up here, I could solve for the natural log of x and substitute that in. But then u divided by x is the natural log of x, so I still have an x sitting in there. I'm never going to get rid of all of the x's and get it down to just a u. So this one's not going to work either. So this is bad. This is bad. A better u in this case is going to be what? The natural log of x. U equals natural log x. So then du equals 1 over x dx, which we have. If we rewrite this as 1 over x times 1 over the natural log of x dx. This is 1 over u. This is 1 over x dx, which we have sitting right here. So this integral quickly simplifies down to 1 over u du, which is the integral of u prime over u. So now I can just integrate this thing. The integral of 1 over u du is what? The natural log of the absolute value of u plus c. But u is the natural log of x. So this becomes the natural log of the absolute value of the natural log of x plus c. Here's a question worth asking. Do we need absolute value here? Yeah, but what if I plug in a negative number for x? No. But what if I plug in a negative number for x? No. Actually, what the better answer here, in my opinion, would be is an absolute value around the x. Because once I take the natural log here, I can wind up with a negative number, and then I have to take the absolute value again. So I would think that you'd want to have absolute value here as well, is what I'm saying. But they don't. This is the answer. So I don't know. I'm kind of curious about that. Anyway, this is the answer that you get. And you need to understand that you can't plug in a negative number when you're taking the natural log. And if you do that, when you take this natural log, you'll get a negative result, possibly, which is why you have to include the absolute value here so that you are guaranteed to be taking the natural log of a positive number.